I think it's important for us to communicate to you and to all that the SETI Institute is embarking into an important new phase of the extraordinary work that it has been doing for the last decades. We are engaged in what I call the pivot, and I explain it succinctly by saying that we have been and we are looking outwards to characterize other places where possible life can exist. We are trying to understand how we got there. But I want to, as well as looking outwards, I want to do what I call a judo flip and look inwards and use that wisdom, that knowledge that we are gathering from the cosmos, looking inwards to contemplate our own civilization and how we can use this knowledge to make sure that we are going to stay around long enough so that we can observe if there is indeed life out there. I am privileged to have been asked to introduce the speakers for this session. So after I put my glasses on, allow me to do this. Now, I am, as you can hear from my accent, not half French, Dominique, I'm sorry. I'm half Swiss and half American. But my half Swiss part is going to look at the clock very carefully, and I'm going to make sure that we stay on time. So we have our first speaker is Cardinal DeVito. He's going to speak about mathematics in interstellar communication. He is Professor Emeritus at the Department of Mathematics at the University of Arizona. He's a member of the Emeritus faculty in the Department of Mathematics. He has developed one of the most widely cited proposals for a language based on plausibly universal scientific concepts, and has contributed to several edited volumes on cosmic communication. His other scientific work includes many papers on pure and applied mathematics, and 4 books, Science, SETI, and Mathematics, which is recent, Harmonic Analysis, A Gentle Introduction, 2006, Functional Analysis and Linear Operator Theory, and Functional Analysis. If Carl could come here. I'm going to see the podium. My first question after we are done to ask you if you believe in Platonic numbers.
That might come across. How do I make... Okay. All right. Yes, I'm going to talk about many things. Doug's conferences always get me thinking, and I want to thank him for asking me to come here. But sometimes I think too much, and I have a million questions, and as soon as I get to an interesting question, I'll turn around and do something totally different. So please bear with me. Maybe we'll have time later to discuss some of these things. Many of the suggestions for interstellar messages involve the natural numbers, and you see them there. We all know them. And the immediate question is, do these objects exist outside of our minds, or are they simply human constructs? If they exist, and certainly any intelligence might discover them, they're certainly useful. On the other hand, if they exist only in our minds, how is it we all agree on how to deal with them? I mean, we can't agree on anything, right? Here we are agreeing on the natural numbers. Now, they're so familiar that we overlook some of the subtleties. So bear with me while I remind you of a few things that I think are important. First off, cardinal numbers. The number of objects in a collection is called the cardinal number of that collection. And people have been aware of that for millennia. And the way they tested it was to set up 1-1 correspondences between pebbles in a pile and maybe the animals in their herds, or notches on a stick and maybe their children, or who knows what. No counting is involved. I can tell that there are more seats here than people without counting. Everyone's seated and there's plenty of chairs left over. Now, more subtle is the ordinal property of numbers. they form an ordered sequence, a first, a second, and so on. And this is the property that enables us to count. How did this idea arise? I think it came from the fact that we're tied to the day-night cycle of our planet. When you had to go from one village to another in the ancient world, there was no way of measuring the distance, but there was a way of measuring the time it took you. At the end of each day, you carve a notch in a stick. Now, after one day, of course, you have one notch. After 2 days, you see two. And sooner or later, you might get into your head that this 2 follows 1, and is followed by 3, and so on. Now, we're tied to that cycle. At the end of each day, we go to sleep, you see. And consequently, the day-night cycle, I think, which led us to this rather subtle idea of a sequence, an ordered sequence. And to what extent do the planet cycles enhance the mental development of those on that planet? We have a calendar, we have various things that are involved with the cycles. Now, there are several kinds of signals. Let me start with attention getters. People have suggested that we send out signals that are obviously artificial. Several suggestions have been made. The Fibonacci numbers, which you see on the first line. Fibonacci was concerned about breeding habits of rabbits. He said if we had a pair of rabbits who take 2 months to mature and after that produce a pair a month, how many pair would we have each month? And as you see, after the first 2, the next number is the sum of the 2 before it. So 3 is 2 plus 1, 5 is 3 plus 2, and 8 is 5 plus 3, and so forth. They're simple, and they arise in a great many biological situations. And they do measure some physical phenomena as well. Now, in the movie Contact, the aliens call attention to their messages by sending a sequence of primes. Now, primes are going to come up again in just a moment. So let me remind you, a natural number larger than 1, whose only factors are itself and 1, is called a prime. And there I've listed the first few of them. If we got a sequence like that, it's hard to imagine a natural process that does that. We would almost immediately say that's artificial. Then you have another type message, which I call Drake type messages or Drake postcards. Someone like Seth was talking about hello, how are you kind of thing. This has, well, it's based on the natural numbers, but a little more knowledge than just simply counting. The key is the fundamental theorem of arithmetic, and that's that any natural number larger than 1 is either a prime or it can be written as a product of primes. And those factors are unique. You see 1001 I wrote there as 7 times 11 times 13. Those are the only primes whose product is 1001. And anybody factoring that into primes would get the same numbers. Now, in one of Drake's messages, one of them suggested there were 1,271 zeros and ones. Since you can't figure what else to do, you count the number of symbols, factor it into primes, and you see it's 31 times 41. Now, why 2? Well, they're trying to tell us that the message is two-dimensional. In other words, the picture. And by arranging the zeros and ones in rows and columns, we get an array that tells us a considerable amount about the sender. This is all well known, I'm sure, so let me just stop here with that. But they're based on the fundamental theorem of arithmetic, which may or may not be known. We don't know. Now, what about languages? Well, let me talk about 2 attempts at languages, Hans Freudenthal's Linkos and the attempt I made with my colleague Richard Early. We start with the natural numbers, as does Freudenthal, and we develop simple linguistic concepts. Now, if you're not familiar with it, it looks difficult, but because it's abstract, but if you get into it, you'll find that these languages are really quite simple, and you can say very little with them. The amazing thing is you can say a lot of mathematics with them, surprising amount, but I'll come back to that. Freudenthal went on to discuss human behavior, human qualities like intelligence and so forth. He wanted to set up a complete language for what he called cosmic intercourse, and presumably the 2 races to engage in a dialogue, which might not be really physically realistic. Early and I went in a different direction. We figured it was so easy to shoot down ideas that we figured it would be best to take an idea, work it all out, dot all the I's, cross all the T's, and see if somebody could do better. We wanted the two societies in contact. We were assuming we were in contact with another society. Well, they have the radio telescope, presumably some science, and they're interested in us, consequently, the outer universe. So they would be interested in scientific information. And we'd like to communicate precise, quantitative scientific information. So how could they do that? How could we do that? Well, they'd want to know the radius of our Earth, its mass, the energy output of our sun, questions like that. And immediately you see the problem. The mass of the Earth is in kilograms. The energy maybe is in calories. What's a calorie? What's a kilogram? So the first thing you have to do is figure out a way to get across the human measurements, units of measurement. And of course, to do that, you assume a little more. Not the fundamental theorem in this case. We assume some chemistry. Mainly that they would know about the chemical elements, which are universal. They'd know about the periodic table, the Avogadro number, which is so fundamental, and there are many ways to measure it, and the properties of gases. On the basis of that, we reached a point where we could exchange this scientific information. Now, this is where Early and I left it. Some years later, I looked back at this, and I thought, well, maybe a dialogue is not the thing we want. Maybe the realistic thing is to send out a pair of monologues, so to speak, to let the other races of the universe know that we exist. And much as the ancient peoples have done here, right? We learned from the Romans and the Greeks and so forth. And to a certain extent, they live on in us. And maybe that's what SETI is about. Now, Al, in his abstract, raises the point that people seek to inform future generations about their lives. SETI may be the ultimate expression of this. Maybe that's what we should be thinking. Well, in summary, the natural numbers may be known to any race that has the radio telescope. We may use them as attention getters, like the Fibonacci numbers or the primes. We may use them to create Drake-type postcards, assuming the fundamental theorem. They also enable us to construct a simple formal language with which we can communicate a great deal of mathematics, should we decide to do so. Now, something that's often missed, you see, our mathematics says a lot more about the human race than is generally realized. It's sort of like our music and our art. The only thing is mathematics has a habit of becoming useful, but it really is not concerned with the real world. It's concerned with the world we created, and over centuries we created it, and it has a lot of our stamp on it, the human stamp, so to speak. Well, to go further, we assumed further knowledge. Now, how about new directions? Well, here, David Dunner, who is Willis, suggested that instead of common knowledge, we seek common experiences with extraterrestrial intelligence. And I thought about that, and two such experiences occur to me. One is cycles, and the other is symmetry. Cycles occur in practically any astronomical environment. I mean, planets circle their sun, they tend to rotate, they may have a satellite of their own. And many minerals are symmetric, crystals and so forth. Many insects are symmetric. Now, these two phenomena have interesting but very sophisticated mathematics associated with them. If our contactees have developed their own mathematics based on symmetry and cycles, then we might have here a way of gaining insight into their mental processes. See, the mathematics is about the same thing. It's about symmetry, it's about cycles. And it should be mutually understandable. But the difference in the way we approach these things may be telling. Maybe give us some insight into the way they think. Whether or not we can communicate this is hard to say. The mathematics there is fairly sophisticated. Oh, let's see. Here is something that has been on my mind for some time, and I don't know. I think this audience may be the best to discuss this kind of thing. Lamarchard and Lomberg, in one of their papers, made this statement. There's a strong link between aesthetic principles and the perception of scientific truths. Some consider aesthetic symmetry as a criteria of truth to be employed when choosing between one theory and another. Now, the physicist Paul Dirac made similar statements. See, a physical law must possess mathematical beauty. He also said that a theory with mathematical beauty is more likely correct than an ugly one that fits some experimental data. Einstein, Hermann Weyl, Chandrasekhar made the same statements. And in pure mathematics, we have G.H. Hardy in his book, Mathematician's Apology. He says beauty is the first test. There is no permanent place in the world for ugly mathematics. Now, I don't know, is there something universal about our aesthetic sense? I don't know. Something I think we might want to discuss. Now, some unanswered questions. Well, there are plenty of them. I've raised a whole bunch of them. What is the goal of interstellar communication? Are we seeking a dialogue? Do we seek only to exchange scientific information? Or are we trying to leave a legacy of our existence with the other intelligences in the galaxy? If so, what is our legacy going to be? What is it we want to be remembered as? You know, a warlike race, an intelligent race, a scientific race? What, if any, what role should human aesthetics play in interstellar messages? And what experiences might we share with an alien race, and how can we use those experiences to enhance communication and perhaps mutual understanding? Those are the questions I'd like to address here today, perhaps later on if we have some time. Now, do I have any time left? 3 minutes? You see, the mathematics of cycles, well, there's something called roots. You see, any non-zero number has 2 square roots, 3 cube roots, 4 fourth roots. If you look at the roots of the number 1, you get what's called the roots of unity. And they have remarkable properties. And if anybody here who knows something about radio engineering, digital signal processing, and so on, the fast Fourier transform is based on that. I wouldn't be surprised if that would be something known to any race that has the radio telescope. And we might be able to play on that because it has a cycle, like the days of the week or whatever. And they have other remarkable properties. And symmetry, the mathematics of symmetry as group theory, that's more sophisticated and more abstract. You have to sort of take a leap of imagination that it took the human race a long time to do. You have to sort of extract from a geometric figure an algebraic structure called a group and show how properties of the group enhance your understanding of the geometric figure. Those are questions which might be of interest, but to some extent, maybe we're going too far. Maybe we're better off staying right here. All right. That's, I think, the extent of my talk.
Thank you very much indeed. We have 10 minutes for Q&A. I'll ask the first question. Actually, just a remark. I met David Gross. You probably know who he is, one of our Nobel laureates. And I asked him very naively, do you believe that in Platonic numbers? And he actually got angry at me because he does not believe that numbers are Platonic, that they exist outside of our own thinking. And I was wondering if you had any reaction to that.
I'm just surprised.
Okay, if you have a question, please raise your hand so I can share my microphone with you. Anybody a question?
Trying to think how to phrase this right. Kim Binstead, University of Hawaii. We were talking, with numbers. Imagine if you had a species who had evolved in a fairly continuous environment, so maybe cloud-based or something like that. What might their math look like, and what might they consider to be primary symbols?
I don't know. There is a mathematics of continuous cycles, Fourier series, for example. But whether or not you can have a society that's purely continuous and has no discrete mathematics, I don't know. I don't know if you can do that.
Or maybe the discrete mathematics is their advanced math.
Yes, perhaps, that's right. But if you imagine a very intelligent machines, as we've been talking about, they may have just a discrete mathematics that never go to a continuous math, because to some extent, continuous math is sort of the limit. And we can mentally go to the limit, but a machine might see no point in doing that. They may just stop with with the discrete.
Anybody else? You were talking about having numbers coming out of the night and day cycle. For me, it was the count of my ex-wives. It was very discrete.
Thank you. Carl, this may not be an answerable, a good question, or even answerable, but I've been reading old anthropological literature. By old, I mean older than me, from the late 30s and about 1940. And came across a reference to algebra that I'm not really sure isn't algebra. And apparently this algebra was a highly stylized type of mathematics, that was in Japan for a while, and then disappeared, then reemerged in China, then completely disappeared about 1850s. And so when we talk about, I'm not even sure what they mean by algebra in this case, but are there forms of mathematics that once flourished, or at least seem useful, that nobody could make heads nor tails of today, do you think? Or is there such an inherent logic and stepwise progression that eventually people could figure it out? Because we go on the assumption, and think, and I do too, math is universal, but could it be unrecognizable to other people?
Well, it's hard to go back, but it is. See, the literature on mathematics is fantastically vast. I mean, really vast. That's not usually understood. You know, a lot of mathematics that I learned, my students don't know, and it just keeps going like that because the field is constantly growing. There were some attempts to solve equations by radicals, it was called, in the Middle Ages, and somehow the Japanese heard about that, and they were cut off from the rest of the world, and they went very far with it. And when we suddenly opened up to Japan, we learned that they had done things that we were gone in different directions, but they had just kept plowing forward. They were solving equations of the 100th degree, for example. Now, maybe that's the sort of thing you're talking about. But to go back and read old mathematics, you can do it, but sometimes you just get very annoyed at the way they write, you know.
Thank you. Just to add to that, I once made a film about Japanese mathematics, and I was doing some reading. What they would do before Japan was opened in the 1860s or whatever, or actually in the 1600s, the Dutch came through. They were attacking calculus problems. We're trying to find, the area under a curve or the volume of some shape. And the mathematicians in Japan would post these problems on, signs essentially outside their homes, and anybody who wandered by could. It's sort of like it's sort of like that movie actually. But as soon as they developed specialized methods for doing these individual problems.
Yes.
But as soon as the West was open to them and they saw what Leibniz and Newton had done in calculus, they threw all that out. So I think that that one example at least suggests that there is really only one mathematics that makes sense, that's beautiful in the sense of being universal in general.
Yeah. Well, you may be right. I like to think it's right, that it is beautiful mathematics. A lot of people think that's a misnomer, contradiction in terms, but I don't think so. How much the aliens would know is a question. I mean, will they know everything we know? It's hard to know that, Well, some of our mathematics is very practical, and you think, well, if we can, the way heat travels through metals and so forth, there's mathematics of that. And if someone else is solving the same problem, presumably they'll come up with the same math. Maybe.
Sherwell Stinson, can I just ask a question maybe from out of nowhere? How much technology do you imagine that you could develop without math? If you just had experience of how things work, how much could you build and how far could you go without a separate field of mathematics?
Well, I think you can go pretty far. If I think Edison is an example of that. He seemed to just do all sorts of experiments, and some of them worked and some didn't. But he was constantly experimenting, and I don't think he had that much of a background in science, to be honest. But he has many, many patents, over 1,000 patents. So you can probably go fairly far in technology.
Thank you very much. Any other question? So we'll start again in 2 minutes or 3 minutes with Marek. Thank you, sir.